Hello, everybody. I hope you are feeling well today and you really are enthusiastic about online seminars, especially those on Saturdays. As Stefan said, we are moving from theoretical computer science to more applied one, but still we will find a petri nets here in my talk. And what's important, there is a lot of nice mathematics behind all these problems, both discrete mathematics and continuous, and a lot of smart algorithmic techniques. But what is the most important for me, and it gives a great pleasure, is to work with real data and to so at least try to solve real life problems. So I will try at the beginning to introduce some basic concepts in mass spectrometry, and then I will touch on the three problems, and at the end some open questions and open projects. Well, I will start with a few words about my research in general. I can summarize it like computational tools and mathematical models for molecular medicine. This colorful mind map illustrates different projects I'm involved in during last years. So it's maybe not humble to say, but I'm quite experienced in supervising young researchers. So the number of PhD theses completed and in progress are also depicted here. And as you can see, the biggest tree, sub-tree, is the red one, and it deals with proteomics, and we will focus on these proteomics applications. What's the next here? Well, okay, the mass spectrometer is in fact a very sophisticated device, but for our purposes enough to know that it measures the mass of a charged particle very accurately. And here at the bottom, I cannot do it bigger. At the bottom right corner, you can see the example of mass spectrum. And even for a single molecule, for a single substance, it looks like a bunch of peaks. It's not a single signal, but a bunch of peaks. And the reason for that is the existence of stable isotopes in nature. For example, all proteins are composed of only 5 elements like carbon, hydrogen, nitrogen, oxygen, and sulfur, but there are several stable isotopes for each element, like deuter for hydrogen and carbon C13 for carbon. Okay, and this is why when we look at the so-called molecular formula for a protein, it simply specifies how many elements of each kind is in its composition. We can calculate the number of different isotopologues. It means that each choice of a specific pattern of stable isotopes corresponds to one isotopologue. And it's easy to calculate that it's a huge number of such configurations. So now our idea is to simulate this distribution efficiently. So of course you can analyze the real data, but quite often you want to have the algorithm to simulate the spectrum for a given molecule. The first important observation is that the probability of a specific isotopologue differs. For example, the probability of seeing the methane is 1 carbon and 4 hydrogen atoms, and methane consisting of standard versions are much more probable than a methane with carbon C13 and 4 deuter atoms. And how to it can be easily done. if we assume that the isotopes, the variant of isotopes of atoms are independent, and of course we use the proportion of different isotopic, so stable isotopes in the nature. As we can see here, these proportions are not equal. For each element, one isotope, the lightest one, is in fact the most abundant in the nature. Like for carbon, almost 99% of carbons are carbon-12, and so on. Okay, so we can calculate the probability of a given configuration using multinomial distribution and proportion of stable isotopes. Having such probabilities, it's a probability of a one peak. We can now profit from a nice mathematical property, so-called monotonicity. When we look, for example, it's a very, very simple example. We have 200 of oxygen particles, and in this three-dimensional simplex, the point corresponds to one isotopologue. The red point corresponds to the highest peak, the isotopologue with 3 monoisotopic variants. We can see that neighboring states are those with a bit smaller probability. So it's natural to propose the algorithm that is going through this configuration space, and we can generate all peaks in the manner starting from the highest one. And the algorithm is in fact optimal, very efficient, and it gained a lot of interest in the community, and has a lot of applications now. Okay, let's go to another problem related to medical diagnosis. It was a long time ago we analyzed samples from colorectal cancer patients, mass spectrometry samples, a complex mixture of blood serum from patients with cancer and healthy donors. And in such case, the main goal is often to find the so-called biomarkers. It means proteins that can discriminate between groups. And we also intended to find the biomarkers, and we were very surprised that after analyzing the data, we could find a perfect discrimination. And we were even more surprised when we realized that when something wrong happens, namely the fridge was broken, our discrimination was even better. What happens? It turned out that what in fact discriminates so well between samples is not a specific protein, but the process called proteolysis, the activity of proteolytic enzymes. And when the fridge was broken, this process was not stopped in low temperatures, and we can do better, in fact. So we proposed the first model of proteolysis in mass spectrometry data in proteins. And you can see here the Petri net, which corresponds to this process. There are states corresponding to peptides, and also transitions corresponds to specific enzymes. We can, after model the flow, the dynamics by means of Markov chains, and to also calculate the stationary distribution and the evolution of time using ordinary differential equations. And it was quite nice, especially as the same approach can be applied to another fragmentation process which happens inside mass spectrometer. It's induced intentionally to cut molecules into smaller parts. It's always nice to have a smaller parts. It's easier to identify such parts, and it's easier to quantify them. And this is why we have so-called collision-induced dissociation, when some ions are introduced into mass spectrometer to induce the collisions and cut into smaller pieces. And the same mathematical approach from a previous fragmentation can be used here to model what happens in mass spectrometer. And it's really nice because the results of our analysis can be used to optimize the experiments. And now, currently, we are establishing the collaboration with the greatest supplier of mass spectrometers, Bruker, and I think it would be really challenging and fruitful to develop these ideas further. Okay, so at the end, I would like only to mention about the new approach we propose in mass spectrometry, namely to apply the optimal transport to compare spectra. You can see here two color spectra. The top one is from apigenin, a small molecule, which looks like here, and the bottom from quercetin. These two molecules are very similar. They differ only by 2 oxygen atoms, in fact. The idea of Wasserstein matrix, the metric is very popular in computer science under the name of Earth mover distance, especially in image recognition field. But here we talk about optimal transport, and we want to transport the masses in mass spectrometry, exactly masses, from one spectrum to another. And this is illustrated here by colors. It means that this yellow peak is sorted into this yellow peak. This big blue peak from apigenin is smoothed through all the small peaks in quercetin and so on. The transport is optimal in that sense that it minimizes the work. It means the mass multiplied by the distance we have to move the mass over the distance. Well, this applications, and now we are trying to apply it to mass spectrometry imaging and also to analyze nuclear magnetic resonance spectra, which are a bit different from mass spectra, but still very challenging. Well, so there's a lot of open problems, a lot of projects, and if you are interested in real life applications, you are welcome to join our group. So thank you.